Hi, I'm Frank Gagnon for Windu Energy. I have done a small presentation last week for Canada Solar, and it have not. We have problem with Zoom, so I make this recording for those who have missed the presentation. So there's two parts. The first part, I talk about the problem with small and medium-sized wind turbine. There's so many crooked projects, so many unreliable projects on the market that it's difficult. And then the most important part, I'm going to show how we can improve the penetration of clean energy everywhere. Okay, small and medium wind. There is so many projects offered very often from China, but not only from China. People think that they have an idea, they build something and it's work and it's fantastic, but in fact it's not fantastic at all because there's a lot of problem. It's not intuitive. There's a lot of problem that appear when you put it on the market, when you work with that project. For example, those projects here, they are not adjustable to the wind direction. So most of the time they face one side of the building, and when the wind is in front of the building, directly in the front, those wind turbine works, they produce some energy. But the moment the wind comes from sideways, backward, there's no energy production. So at the end, you have energy 20% of the time. So it's useless. It's useless to install this kind of project. Sometimes even, you see the last one here, people do not understand the difference between wind and turbulence. There is no wind produced by a car and truck. It's only turbulence. You cannot make significant wind energy with that. That's not possible. There is Darius and Savonius wind turbine. Savonius wind turbine are very, very simple engine, but the wind push on the plate or on curve, and it cannot be efficient for physical simple law that I will not explain here, but the efficiency is 15–18%. So it works, it produces energy, but the amount of energy is so small that it's not usable. Darius wind turbine can be very efficient, but there is a lot of mistake you can do. For example, on the center part, you have more than 3 blades on the same level. When you do that, each blade will run on the turbulence of the precedent one, and it's just reduce the efficiency by 30–40%. So it's useless. The more blade, less energy. It's not correct. If you make twist blade, that's interesting. That's another project. You see that on the market, few items. It's you have 1 degree difference in the angle of the blade, reduce the capacity by 10%. So it's very, very difficult to have an accurate twist blade like that. Well, that's why most of the time it doesn't work properly. And the worst is the top one. They try to match together Darius and Savonius wind turbine. There is absolutely no common linear relation between those two wind turbines. So each one borrow the other one. It reduces the efficiency. And you saw many of that on the market. It's no good. At Windu, we produce Darius wind turbine. Darius wind turbine is very simple engine, very simple wind turbine, but the design of it is not simple. We have done thousands of computer simulation to achieve optimization on the blade, on the size and everything. And under the field test with different prototype, because what you see on the computer simulation is different than what you see on the field, and you have to put both together to finalize the way you're going to manage, the way you're going to produce, and the way you're going to manage your wind turbine. One important point is that wind energy is soft energy. Before they call that clean energy, they call that soft energy. You need to catch a good quantity of wind to make significant production. Yeah, the giant wind turbine, a very mature market, they understand that very well, and that's why you see always bigger and bigger wind turbine. So at Windu, we have chose for the same 20 kilowatt modular wind turbine that we're going to produce. We have 4 sizes of turbine that we're going to put on top of it. Depending on the wind profile of where you install the turbine, you're going to have different options. So For example, the largest one, the model number one, which is done for low wind side, you're going to produce 20 kilowatt with wind of 25 kilometers per hour. This means we can have on an island of Montreal, for example, a very efficient wind turbine that's going to deliver. To make a comparison, the giant wind turbine, they're going to use 70 to 90 square meters of turbine for the equivalent of 20 kilowatt of energy production. We go from 115 to 300 square meters. So it's much bigger, but we're closer to the ground, so the wind is a bit less efficiency. So one with the other, we're competitive. We're very competitive with giant wind turbine. Okay, the main question of this presentation is how we can improve the penetration. The problem with wind energy and the solar energy is that they are random. One day you have some, another day you have a lot, the third day you have nothing. And we have to find a way to manage that, to optimize the capacity of those energy resources, and this is what we propose. So if we take the first part of the graph, on the left, it's what you see in real time with the wind turbine. It could be an hour, it could be a month, it could be a year, it's the same thing. You can have a profile of a site, the wind profile of a site, and based on the wind turbine or the wind turbine part that you install of it, you can make an histogram of the energy production that you're going to be able to produce with that. And from there, you can build business model. So what we propose is oversized wind farm. What is an oversized wind farm? A standard wind farm for us, for make a 1 megawatt connection on the grid, we're going to use 50 of our 20 kilowatt wind turbine. And we're going to supply, like the giant wind turbine, we're going to supply 30–40% efficiency on the megawatt connection. The grid is used to work with that, but it's difficult. It's difficult to manage for the grid. Now, an oversized wind turbine, we can say, okay, on the same 1 megawatt connection, we're going to put 100 wind turbine. So what it's going to do, we have the same profile of wind, the same profile of production, except it's the double. So sometimes you're going to have more than 1 megawatt, and you're going to have to lose this energy because you have a 1 megawatt connection to the grid, so it's lost. It's not a big amount of loss, but it can be 10%, it can be 25%, depending on wind profile and the wind farm. The big advantage of that is that you supply now, instead of 30–40%, you supply 50 to 65% of the connection that you have on the grid. So it's much more efficient for the grid manager. You have more energy from the same connection, and of course it costs you a little more to produce that because you lose some energy, you lose a small amount of energy. So if your wind production costs you with 50 wind turbine 3 cents per kilowatt hour, now if you have an oversized wind farm, it's going to cost you 4 cents per kilowatt hour because you lose a part of your electricity. If you sell the electricity to the grid at 5 cents, it doesn't work to do it. But if you sell the electricity at 8 cents, well, then you make more money on the same connection, on the same deal with the grid. So it's both at the advantage of the grid manager and at your advantage because you make more benefit. Now we can go over that, and we can say we're going to put 200 wind turbine on the same 1 megawatt connection. Of course, now we have a very different profile. We offer to the grid manager 65 to 80% of the capacity of the connection. Now it's becoming very, very, very efficient. It's much easier to fill the empty part. And you have a lot of energy that is produced there, but that you cannot give to the grid. So if you lost the energy, of course, it's very expensive. But now you have enough to say, okay, we can use this energy to do something else. So if we have 3 cents electricity with the basic wind farm, we still have 3 cents electricity for the electricity that we deliver to the grid and 3 cents for the electricity that we're going to use on site. Or it could be 2 cents on site, 4 cents for the grid manager. You can manage many business models with that. So one quick example, if we have a 2 megawatt giant wind turbine or 100 of our wind turbine on a wind site of 6 meters per second, we're going to offer about 43% of the nominal grid connection. Whatever what we do is the same thing for the giant wind turbine, and similar principle can be used for solar also. Now from there we can manage a profile, we can manage the use of the electricity based on what we know what we're going to have over here. And we build business model. A good example of that is microgrid on Norton Village. If we install 2 megawatt capacity, 100 wind turbine, or the giant one, and the average use of the village is about 500 kilowatts. Sometimes it's going to be 300 kilowatts, sometimes it's going to be 700 kilowatt, but an average it's 500, so it's easier for us to understand how it's working like this. Already we're going to supply 70–75% of the electricity demand directly from the wind turbine to the grid of the village. So it's already the most important part of the electricity use of the village. Now, if we take the first part of the extra, the surplus, we put that on batteries, and we use the energy that we put on batteries to cover a part of the empty space when there's not enough wind. So we can add another 10–15% of the demand via those batteries. So we going to supply clean energy instead of diesel for 80–90% of the need of Norton Village. Still, there is some days that you're going to need diesel, the generator that is already there, and think that we're going to be zero carbon emission in 5 years, 10 years, 20 years is not relevant. It's never going to happen. We're always going to have to use some fossil energy, but we have to reduce that to the maximum. With this model, we can do it. As you can see, it's leave us a lot of electricity for the heating for the village. So the best way to use overcapacity is to produce heat, because it's easy, it's very efficient, and there's a lot of things you can do for with a high temperature heat. There is some example here. You can take the time to see the slide after. All those are mostly done, the heating is mostly done by fossil energy. We can replace that by surplus of wind or solar energy. Now, how does it going to work on the Norton Village? We're going to install an overcapacity wind farms, and there could be some solar too. There's some village that they have hydrogen system also, and they still have the genset. So we put all this electricity on a battery loader with 3 maximum power point traction system on it, so we can maximize the input and load some batteries on that. From there you have the storage, and you have the management of the energy. And the energy supply to the village is supplied by an inverter coming from the batteries. And this is very important. This inverter is sized to the grid capacity. Why for? What is the plan? Let's say that we have a wire on the village that is have a capacity of 1.5 megawatt. The use of energy in the village, the use of basic electricity, will vary continuously from 300 kilowatt to 500, 600, 800 kilowatt. Okay, this is basic supply. If we load the network with 1.5 megawatt, there's a lot of more supplementary electricity that we can bring to the home or to the other building to store heat. And like this, we can transfer a lot of this storage above the batteries. Of course, it's not every day that we're going to have enough clean energy to store on the heating system. Sometimes we're going to have to make choice. And even sometimes there won't be enough sun, there won't be enough wind. So then the battery is going to take in charge part of the electricity need, and it might come to be the diesel also. So the management system will see how much energy is available from each source. Random source, wind energy, solar, hydrogen. And if there is too much energy produced by the wind and the batteries are full and everything is full everywhere, you can reduce the production of the wind turbine. You have 200 wind turbine, you cut 50 wind turbine, 25, 100 wind turbine, whatever the need, and you stabilize the maximum, no overproduction. And on the reverse, if you don't have enough clean energy, then you can start the genset to load the batteries, and when you have a lot of batteries with a genset, the genset is more efficient because it's always work at its maximum capacity with no loss, which is not the case. Which is not the case in general. There's a lot of electricity loss when your electricity only comes from genset directly to the house or to the other building. And on the other side, the same management system have to know how low are the energy storage in the village. So if you have, for example, the Steffi furnaces on 100 house in the village, the Steffi furnaces, by the way, sponsored by Hydro-Québec, can store 80 kilowatt hours of heat. So if you have 100 of them, you have 8 megawatt hour of heat that you can store within the village. And the same thing for commercial building, you can have larger energy storage system. We're going to see it's going to be GSG here. And it could be, for example, 3 megawatt hour system for a total of 15 megawatt hours. So altogether, we are more than 30 megawatt hour of storage. We start to have something very consistent, very reliable to store the energy and maximize the use of the clean energy. GSG energy, very rapidly, we store heat at high temperature. When you make heat with electricity, it's very, very efficient, 90% efficient, and you can reach relatively high temperature. There's a very small loss on your system if it's well insulated. And when you have high temperature heat, you can transfer this heat with very high efficiency also. It's very simple to transfer the heat. And the GSG system is scalable from 250 kilowatt hour to 50 megawatt hour for a very large building, for example. So thank you for your attention, and if you have questions, do not hesitate to post it. I will answer as fast as I can. Have a good day.